It's great to be here. I mean, this is almost like my second home. My folks lived in Canaan, which is 10 miles as the crow flies. What I'm here to talk about today is, with a little bit of edit to the title, is describe how and some of the work we've done in the last 30-ish years on studying cultural heritage using modern imaging technologies. And if you look at the pictures, you can see some of the results that we were able to get. But the change, I've changed it from golden age, given what's happened in the last week, to the age of lead, because all of a sudden the entire situation has changed in the areas that we're trying to do studies in. And I'll describe a little bit of that as we go along. The reason for the title change is the effective dissolution of the National Endowment for the Humanities, which has happened just in the last couple of weeks. And but I will say there are reasons to look back on history and see how people have reacted in similar situations, and particularly people in the local area here. And so as I was driving from Rochester yesterday, listening to satellite radio, the political shows, I was getting angrier and angrier, and it encouraged me to sort of look up to see people who've had to deal with similar situations before. Anybody know who this is? This is an engineer, or was, mechanical engineer, born in Dartmouth, Vermont, so right nearby. He's a model that we can use for inspiration. He was the president of Jones & Lamson Machine Company in Springfield. And if you're not familiar with the machine fabrication business in Springfield, you probably should learn about it. That company was, we've been coming up here on family vacations for 50 years from the DC area. And so I remember when J&L was actually running, actually had been in there when it was operative. This guy was a friend and colleague of James Harkness, and that's a name that I may or may not be familiar. He at one point was the governor of Vermont, and he was the guy, John probably knows about this, built the turret telescopes that are at Stellafane and at Harkness House down in Springfield, and if you ever want to go have a fancy dinner and combine some science with it, that's a place to go. I think it's still open. This guy married Harkness's daughter, Helen, and later became a U.S. Senator from Vermont, but he got a start in the machine business. And he was one of the first to stand up to the situation in the 1950s. In that respect, it was McCarthyism. This is Ralph Flanders. So a local engineer who had a lot to do with sort of writing our course at a time when we were going astray. Here's the second guy. Anybody know who this is? My sister knows, and John knows. This is another guy who stood up. He was also an engineer, electrical engineer born in Craftsbury. Designed the Vanguard 1 satellite, which is the oldest payload still in orbit. So there it is on the table with astronauts in the background. Later had the key patent of what we now call the Global Positioning System. So there he is getting the National Medal of Technology. So why does he fit in this category? Well, he retired to New Hampshire, and he got upset at the administration down in Concord. So he ran for governor against the incumbent governor at that time. And I remember I was in grad school in Arizona at the time. He called me up and said, asked if I would be his campaign manager while I was finishing, so I didn't. But his comment was the only thing worse than losing would be winning. He ran against John Sununu, that's Dad. So there are engineers who have stood up against the kind of situation that we have now. And I think we should all take some inspiration from that. Here's another guy that I take inspiration from, who I'd be surprised if any of you know. This is Will Knoll, who passed away last year, tragic accident in Edinburgh. He was definitely all of those adjectives. He was the curator of manuscripts at the Walters Art Gallery, later the Walters Art Museum, in 2000 to 2012. That's where I got to know him. He was the driving force behind imaging of the Archimedes palimpsests. And we'll see probably more than that you care to see. And he then moved on to Penn, where he was the founding director of the Schoenberg Center for Manuscript Studies. And then he went to Princeton, where he was the librarian in charge of their special collections. And we interacted for 25 years together. But he was a real inspiration to this work. Okay, so what am I going to talk about? How we can use modern imaging technologies to recover important information that otherwise might be lost from cultural heritage. And my feeling is, with that, we can recover things that we didn't even know we had from collections that already exist, and that suggests we might have a new golden age of manuscript studies. The problem, of course, is we have to have funding to do that. Fortunately, there's still funding in Europe. So these new technologies primarily include spectral imaging. So we image in a variety of colors of light. This is not new, but the technologies are, so we can do a lot more stuff. And then I'll also talk a little bit about X-ray fluorescence imaging, particularly with regards to the Archimedes. And this is something that we continue to do as well. And then I'll talk about some projects. And I have many, many more slides than we can possibly do in an hour. So probably should only emphasize the ones that people might find of interest. So these are sort of the technologies. Why don't we just skip that? We'll get to the ones we use. The idea of using different colors of light to recover writings from manuscripts isn't new. And in fact, the first example that we made really to find a photography for documenting historical cultural heritage was by the famous Smith sisters, Agnes Smith Lewis and Margaret Dunlop Gibson, the Sisters of Sinai, a book that you can easily locate. And so they documented manuscripts at St. Catherine's Monastery. Pringsheim and Gradovitz, Pringsheim is a well-known physicist, did the first example I've been able to find of multispectral imaging of erased and overwritten manuscript, a palimpsest. And then it was later done by this interesting guy, a monk, a Benedictine monk, Raphael Kergel, who did some really interesting stuff using ultraviolet light. But then he left the order, got married, had kids, and became a Nazi. So here are the Smith sisters. This is pictures on the dining hall wall at Westminster College in Cambridge, because they had a lot to do with supporting that college. And there's one of their photographs. You can tell it's a palimpsest. You can see it was erased and overwritten. And you can also see the thumb up in the corner, which I suspect is probably the librarian at the time, Father Galaction. So this would have been back 1895-ish, something like that. So there's one of the early examples of technology. Then these two guys came up with a way to actually improve the readability of it. Pringsheim was well known. He did important measurements of the radiation from a black body that helped Max Planck come up with develop the quantum theory, among others. And so here's the only example of result I found from them. They took two images under two different kinds of conditions, two different emulsions, two different illuminations. Here's the first one, here's the second one. And you can see in the first one, you see both texts. The later, what we call the overtext, and the earlier, the much fainter undertext. In this image, you only see the overtext. And I found these long after we did the Archimedes work, and what they did is so comparable to what we did. It was kind of embarrassing. So then they took that second one and made a negative out of it, made these on transparencies, sandwiched them together using an astronomical imaging tool to be able to do it, and then photographed those, and pretty much all you see is the undertext. We would be proud of that. these days. That was a terrific result. Then Kergel came along in the 1910s and did the same thing, but also used ultraviolet light. He had a mercury vapor arc, and then he had a little cavity that he could fill up with liquid as his filter to remove the ultraviolet before it got to the lens. So the clever things they were able to do. Here's the before, and here's the after. And they actually published a book, which we found a copy of on eBay for $500. So this was a book of those results, and if you look on the end of it, it says volume 1. They clearly plan to do multiple volumes, but if you look at the date of that book was 1913, so that explains why they didn't have any others. But later on, they actually advertised palimpsest imaging, very much what we do, and you could buy their services to get images without using chemical reagents to retrieve the text. So again, it was just very interesting, similar to what we're doing. Okay, so now let's move to the present time. The playing field, the technology has advanced quite a lot, as I'm sure everybody's familiar, in the last 30 years. So the playing field has changed, and we can do a lot of things now that we couldn't really even imagine doing even 25 years ago. Why do we care? Because the need to preserve history. One of my colleagues did a census of libraries in Europe and came up with the estimate that there's 60,000 manuscripts alone that would benefit from imaging. That, to me, that's probably an underestimate. It's probably more than that, just based on the fact that we go into a collection and we'll find palimpsests they didn't even know. St. Catherine's Monastery is one example of that. And we need to do the imaging, if for no other reason, to make sure we have the manuscripts documented against the external and the internal threats. Fortunately, the technologies and the expertise are spreading. We're trying to do that. We have an inexpensive system that is designed to be built by individuals for under $10,000 US, and those are available. We had a conference about that just a couple days ago. We had participants from 4 or 5 different places in Europe and several places in the US. We also have the high-end system that's ballpark of 150K that are available in several places. And new systems are planned, or as I say, were planned until last week. So it's kind of a rough time right now. So here are the palimpsests. Here's where we focus most of our effort, on these erased and overwritten manuscripts, so-called palimpsests. The one on the left is the Archimedes, and that one will go into some detail. Yes? Would you like to have the lights turned down a bit? That would certainly be fine with me. I'll let Amos do it because. But Eric, thank you for pointing that out.
Yes, thank you.
So the places we've done it, probably, that's probably not as much interest as the map. So in the last 20 years or so, these are the places we've gone to image manuscripts. Typically, we're focusing on a specific one, but in some cases, like at St. Catherine's Monastery in Sinai, we just went over to image everything they had. And we're not done yet. So what we're trying to do is take pictures of the manuscripts under a variety of different wavelengths of light, visible wavelengths to see color. We can get more accurate color renderings than is possible with your standard RGB sensor. But we also use invisible infrared, which is helpful if we're trying to read through damage, particularly charring or darkening. And then, of course, we use ultraviolet to try primarily to generate fluorescence in the parchment, make the parchment glow, and if it, it will enhance the contrast with any text that had been erased. And the technology continues to advance, so we're getting a wider range of sensors. So we're able to get more bands. And here's the reason why we care, because the human eye only sees the narrow band compared to your standard silicon sensor. And of course, there are other kinds of sensors too. This is just the one that is most common. So our current system, we use light-emitting diodes as the illumination, which generate the colors of light by electronic transitions and not by thermal interactions. So they're cool, they are much less potential for damage. We use different imaging modes. Reflection is the obvious one. Fluorescence, as I mentioned, the page glows, and we'll image through different filters, and then transmission. And all of these are important in certain situations. We use a special lens that maintains focus across the wide range of wavelengths that we image. And that's arguably the most important and also most expensive part, other than the sensor itself. And our current sensor is a 150 megapixel CMOS, complementary metal oxide semiconductor, which allows us to get very high resolution images, and still maintain pretty much the dynamic range. But on occasion, we will bin it 2 by 2 to get be able to count 4 times as many photons to get better dynamic range. So there are our illumination, and so on the left are the bands that we use for reflection. On the top and the center, the bands we use for fluorescence, so we'll illuminate with those, and then we'll image through 6 different filters. And then at the bottom are the wavelengths we use in transmission. So there's just stepping through, gives you some idea of what the colors look like when we do the imaging. I mentioned we have this inexpensive system. We call it MISHA, multispectral imaging system for historical artifacts. It's open source. The software is open source. You can put the system together for under $10,000. $6,000 or $7,000 is probably more realistic. And even though it's an inexpensive system, the capabilities are comparable to what we did to recover text from the Archimedes palimpsests, and I'll tell you about that. So this came out of a student project. Kevin Saka, who's just finishing his PhD at University of Colorado, and is just starting at Southwest Research Institute. So there's the website if anybody's interested. Like I said, we've got about 20 systems. A couple days ago, we had Worldwide MISHA Day, WMD. Want to give that acronym a positive meaning. And we had presentations. It was all on Zoom. We had presentations from Paris, Dubrovnik, Vienna, Bogota. And we had this follow-up grant that was awarded, $350K by NEH, awarded in January, and just last week we got the termination notice. So, a downer. So here's sort of the schematic of how we do it. We'll have a camera with a lens, that fancy lens, much fancier than portrayed here. We'll illuminate with ultraviolet, and we'll get an image of the ultraviolet light. We'll illuminate with blue, get a blue image, green, red. These are actual images of the Archimedes, in fact, and infrared. And you can see the variation of the response over that. And then we'll try to find combinations of those images that enhance the visibility of the text. Here would be the situation with fluorescence. So we put a filter in front of the lens, and we illuminate with either ultraviolet or blue. And when we illuminate, we get reflectance off the surface of ultraviolet, but we also get fluorescence from within the parchment in blue, green, and red, other colors too. But and the farther away the wavelength gets from the wavelength you're illuminating with, the less response you get. But oftentimes that's where the interesting stuff is. So that's the reason for the change in thickness of the arrows. And so we'll get the images of different colors that way through the different filters. And again, we will include those in the combinations. And one thing that's occasionally useful, when it's useful, it's spectacular, is we'll illuminate with infrared from the back of the parchment and illuminate and recover. And if the ink has eaten away on the parchment to thin it, the ink may be gone, but you can still see the thin spots. So you can see where the ink was. Okay. A little bit of physics. The image quality can't be perfect. We have diffraction, so the spatial resolution is going to be limited. We also have brightness resolution, which depends on how many photons we count. And so we're always going to get a blur spot rather than a point image. But one thing that's really important is we need the focus to be sharp over the range of wavelengths that we're doing. And if we were to change focus to maintain that, we're going to change scale, which is going to make it a little more difficult to do the processing. The lens doesn't focus different wavelengths perfectly correctly, so we do get some variation in that, what's called chromatic aberration. And I'll skip the depth of field stuff. Here's an example. There's the lens that we first used. So ballpark of $600 US, and here that lens is corrected 3 wavelengths in the visible, because most of the time, most people would use that lens to look at visible light. But so there's a section of the Archimedes at 365, and then change the wavelength into the green, and change it into the red, and now go into the infrared, and you can see how much out of focus it is. So the resolution got worse as we went to the wavelengths that the lens wasn't designed to focus. And so there, the wavelength, the colors of the wavelengths the system had, the F, D, and C, those are the wavelengths that it was corrected at. If we go into the ultraviolet, we're going to go out of focus. If we go into the infrared, we're going to go way out of focus. So that is the explanation of why the image quality changes. So we went to this lens. This was how I paid this was what I used my salary for working on the Archimedes to buy. This was about $7,000. Same focal length, roughly speaking the same size, but significantly more complicated. This was designed by Brian Caldwell, who was a graduate of the Institute of Optics at the U of R, University of Rochester. And it also corrects the 3 wavelengths, but they're much more widely spaced, and it has exotic glasses to make sure we can transmit the wavelengths. But it has almost perfect imaging for over the wavelengths 365 to 900. When I say perfect, what do I mean? I mean, it is in effect diffraction limited. It's as good as you could possibly get physically. So there it is at 365. There's a result at 570. Now we're into the infrared already, and you can see it's still sharp. And now we're out at 940, and it's still sharp. So that's the reason why this lens is important. And this is all stuff that new technology that's come out in the last 20 years. So we're using a medium format camera, not the 35 millimeter format that lens was designed for. So Brian Caldwell designed a larger format lens for us to use. And like I said, this is one of the most expensive parts of the system. This is $25,000-ish, something like that. Okay, so that gives you some idea of what the imaging technology is. Maybe just stop and ask any questions. Yeah?
The sensor that you're buying off the shelf, does that come with the color filter array on it?
The image sensor, it depends on which system we use. We have used sensors with a color filter array, and I'll show you that. But now we use the monochrome sensors without the color filter array. So I got a bunch of different examples, and I'm certainly going to talk about the Archimedes. That was the one that got us started. And I'll even talk a little bit about how we got going with that. But then we have these other ones, other projects as well. There's a much longer list than this, but these are the ones that I made some slides for. So hopefully we'll get through these. So here's the Archimedes. There's what the Archimedes palimpsest looked like the first time I saw it. 1998. It's about the size of a thick paperback book. It had in it the oldest known copies of 7 treatises by Archimedes written down 10th century, 950-ish, probably in Constantinople, probably copied from a scroll because it's in columns. Each leaf has 2 columns of text in it. So that's why they think it was copied from a papyrus scroll. The important part is it has the only known copy of the famous one, On Floating Bodies, Eureka, in the original Greek. But I would say even more important than that, it has the only known copy of the method of mechanical theorems, where Archimedes demonstrated he understood the principles of infinitesimals. He understood integral calculus in 250 BC. And also the stomachion is stomachache. This was thought to have been a tangrams-like game, but it's actually a study in combinatorics. It was overwritten 1229 by Johannes Myronus. We know that. We've been able to read his name and the date off the colophon of the prayer book that was written and dedicated on Easter Saturday. So 177 parchment leaves. You look at the pages, it's in terrible shape. I mean, it's moldy, the pages falling apart, and I'll talk a little bit about that when I get to it. But it also has leaves from other manuscripts. So obviously, they took books apart, scraped the text off, threw the parchments on a pile, and then the scribe came and pulled pages off that pile. And there are other pages that he didn't pull off that are maybe in some other book. So it'd be really neat to find those. But they're erased text from 2 speeches by Hyperides, which were known to exist, but nobody had ever seen them. Nobody in modern times had ever seen them. And a commentary on Aristotle's categories. That's a really cool one. And so it was served as a prayer book in services for about 800 years in a monastery under candles, so the book was covered with candle wax. So Abigail Quant, the conservator, went crazy scraping off candle wax. The value was recognized by Constantine von Tischendorf when he visited the monastery, and he took a page out of it while the monk wasn't looking, and it showed up in his papers, which were donated to Cambridge, where Nigel Wilson, the scholar from Lincoln College, Oxford, recognized what it was, and Nigel is still working on the project. Some leaves were photographed by Heiberg from Denmark in 1906, and in the course of the project, Will Knoll went and found those pictures in the Royal Library. Nobody knew where they were, and he found them. One leaf was photographed at the University of Chicago, and that's an important one because that was one that was covered over in the World War II with one of the forged icons of the Gospels. And so we have a picture of it before and after it was covered. And then the book was put up for auction by Christie's in 1998. And that's when we first came in touch with it. Because of all the different undertext writings, Will Knoll called this the eighth wonder of the manuscript world. So in 1998, in August, my colleague Keith Knox gets a phone call from Hope Mayo, was a scholar working on the auction catalog. And Hope had been at Christie's office in London saying, I need somebody to image this book, which is about to go up for auction. I can't find anybody. She was talking to Meg Ford, who's married to Keith's wife's brother. So Keith Knox's sister-in-law. So that's how we got started. It's because Meg Ford is married to Keith Knox's sister, Keith Knox's sister-in-law. So she called up and said, I'd like you to image this book. She flew up on US Air Express, a twin-engine turboprop, with this book in her backpack that 2 months later sold for $2 million. So there's one of the pictures from the auction catalog, and maybe can you see in that horizontal row, alpha, rho, chi, iota, mu, there's the name Archimedes. That's the beginning of the method of mechanical theorems. And so that we imaged, and that appeared in the auction catalog. And so we felt very lucky to have participated. There we are doing the imaging. This is in the Imaging Science Building at RIT. So the book actually was at RIT. And there we are set up with the industry standard camera at the time. So I'll show you what that is. So there's Keith, who's well known for Knox-Thompson stellar speckle interferometry, but now all he does is this too. And Hope Mayo and Bob Johnston, who was the retired dean of the RIT College of Fine Arts. So he was sort of the guy who got us started. There's the camera that we used, 1.25 megapixels, 1024 by 12, I can't remember, 1280 by 1024. So monochrome CCD sensor. This was state of the art. $20,000 list price when it bought it in 1991. And it had a disk drive, that box you carried around that could haul up to 156 images, and then you had to empty the disk drive, which took hours to do. So that was much different than what we have now. We had a quartz lens that allowed us to focus ultraviolet. So that's what we used for that. So over the course of the project, the technology has changed a lot. There's the DCS 100, the 1.25 megapixel. The one on the right is the DCS 760, 6 megapixel. That's what we did most of the imaging with. And then as the technology advanced, we re-imaged the entire book in 2007 with a 22 megapixel RGB sensor. The Kodak is RGB, that one's RGB, all the others are monochrome. So, and we still have those. But of course the technology has continued to advance to the point where we now use the Q15 from Megavision, which is 150 megapixel CMOS. We just, last month we were just in Vienna imaging palimpsests with that. So the manuscript sold at auction in 2 minutes in New York City. There's kind of interesting side stories with that, which I won't bother to go into, involving the Greek government trying to sue to prevent the auction. Mr. B, the B stands for billionaire, bought the book, and whoever you think he is, he isn't. But he's a sharp guy, and it was important that he bought it. The book obviously caught attention. My director thought what I was doing was a total waste of time until the Archimedes palimpsest appeared on the front page of Physics Today. Then he thought it was important. So after the auction, we lost track of it. We were giving a talk at the Society for Document Information and Understanding Technology in Annapolis in April of '99, so 26 years ago. And we said we didn't know where this book went. We imaged it and we didn't know. And one of the people in the audience said, it's at the Walters Art Gallery in Baltimore. And so I sent an email. We went and looked up the staff at the Walters Art Gallery, and I sent an email to Abigail Quant, and she responded saying, yeah, we've been meaning to call you. So we got to image the whole book. First, we had a competition and imaging of 5 loose leaves. Completely embarrassing when I think what we did for that. But we were successful in getting picked to be the team to image the book. We imaged for 6 years, and we did experimental imaging too. And then we did X-ray fluorescence imaging at Stanford Synchrotron, and I'll show some examples of that. And then we re-imaged the whole book in August of 2007. Took a month, and those are the images we have now, which are still lousy compared to what we could do. And so we have a proposal into the owner to re-image some of the pages. There are a number of publications out there. We'll know, Reviel Netz is a scholar of ancient math at Stanford. He and Will Knoll wrote a book on the project. They alternated chapters. Reviel talked about the manuscript. Will talked about the project. And then we did a 2-volume documentation of the whole project as well. But that's expensive. So I said the technology has advanced over time. I showed you some pictures of that. So we went from 1.25 megapixels to 6 to 22, and then we could multiply that by 4 by sampling at half pixel spacings, so we could get 88. Total waste of time, but we did it. Now we can do 150 megapixel. And when we first did it, we only had 3 light sources, a xenon strobe, tungsten, and, photo floods, and ultraviolet. And we found ways to combine those images to try to enhance the visibility of the text. During the course of the project, we developed a light-emitting diode illumination, and I'll show you a picture of that. So we've already seen this. I don't know why I put it in twice. There's the camera that we used for phase 1, the DCS 760 state-of-the-art photojournalist camera, 6 megapixels, but this did have the RGB sensor on it. And we shot, so there is a page from Stoichion, a double page, a bifolio from Stoichion, and we shot that in 10 sections to get the resolution that we needed, and then we had to stitch those together, which wasn't perfect, but it worked reasonably well. And so we built a XY translation table to do the motion. There's Abigail putting one of the single leaves down on the setup for the imaging. You can see the tungsten photo floods and the ultraviolet lamps. And then we had to figure out how to combine those images to recover the text. And the observation, well, rather than looking at the, let's just go to the images. So there are 2 images of the same leaf, and you can see it's only a small section because of the 6 megapixel camera, under tungsten and under ultraviolet. And the tungsten, you can barely see the undertext in spots. Under the ultraviolet, where the parchment is fluorescing, you get a absorption of the light coming out of the parchment where the ink was, so you can get enhanced visibility of the text. So we had to figure out a way to combine those 2. And first thing we did was we took the red channel of the tungsten, where you pretty much don't see the undertext at all. This is very much like Pringsheim and Gradenvietz. One of their images, you didn't see the undertext. Then the ultraviolet blue channel, you see both, the undertext and the overtext. So this was where we said, let's combine those in pseudocolor. We did an intermediate processing step where we took those images and we did a balancing operation. We looked at a 401 squared section, and we calculated the mean and variance, and we changed the center pixel based on what its value was compared to the mean and variance of the neighborhood. So that sort of flattened the image, if you will. And then we took those and we combined them in pseudocolor. So we took the tungsten red channel and put that in the red channel of an image. And you can see the Archimedes text is invisible. Those pixels are bright. So those pixels are going to be bright in the red channel. Whereas the ultraviolet channel, we put in the green and blue. So the Archimedes texts are going to be dark in the green and blue, and the overtext is going to be dark in all 3. So we're going to get a color difference that tells us which text it was. So here is that pseudo-color image, and you can see the red tint to the undertext. And that scholars got to the point where they wanted all their images to look like this. They wanted to be, most of the time they wanted to see the undertext as well as the overtext, but the color cue told them which text was which. And I saw Reviel Nets take a page he'd never seen before and just in front of an audience and just read it. So there's a magnified view, and here you can see the gutter of the prayer book, and you can see how grimy it got in the gutter. And so there's the ultraviolet image, and there's the pseudocolor image, and particularly look in the decoration and the overtext there. You can see which text is which. If I go back to the original, you can't really even see it. So that was pretty successful. And the scholars, again, got very used to doing that. Here's another example. There's the visual appearance, and there's the pseudocolor. So scholars were able to read 80-ish% of the text from that. We also got the request from the late Bob Sharples of University College London. He didn't want to see the overtext. He just wanted to see the undertext. And Keith and I sat there and said, let's just subtract them. So I wrote a script in Photoshop, and within 15 minutes we had all the images. So there is what we call a Sharpie, where we took the difference, and all you're seeing is the undertext and the magnified view. And that one is okay, but here's the cool one. There you can see the diagram. That was the great thing about this Archimedes manuscript. It had the diagrams in it. And so there you can actually see the labels on the characters. The circles were drawn with a compass, and you can see the pinprick at the center of curvature. So we could read perhaps 80% of the text, but it didn't help on everything. So we had a conference at the Walters Art Museum. They changed their name with ourselves and Mr. B to come up with other ideas, and that's where we came up with multispectral using LEDs and character recognition. Derek Walvard, who was my graduate student, came up with a way to sort of look at filtered versions of the images to figure out what characters were. And the fact that it was a technical text meant there was a very limited vocabulary, so he had a very good idea. If he knew two characters out of 5, he had a very good idea what the other 3 might be. So anyway, let's skip there's the system we used in 2007 using the light-emitting diodes. And so we had the parchment, we had the LED panels, we still had the tungsten and the xenon strobe. And turned out it took us 32 minutes to do each leaf, and we had 350 to do, so that took a whole month. We did the half pixel spacing, which doubled the pixel count. It was a total waste of time, but you can't tell a manager that an image with 88 million pixels is no better than an image with 22 million. So, yeah, so there's the waste of time. I mentioned the LEDs. There's our first LED box. And here we used optical fibers to take the light, kept all the LEDs in the box, and took the optical fibers up to illuminate the page. And then we turned them all on, just for the picture. In real life, we would only turn one on at a time. And there's Keith, who moved to Maui in the course of the project, so he's wearing his Hawaiian shirt. So there is the LED box that I just showed, and on the right is a version that was built a year later, which you may have seen, because that's the illumination for National Treasure Book of Secrets. I worked with a prop guy to develop that. I wrote him some dialogue, but none of it was used. I would love to see the cuttings on the floor to see what they had put in there. There's our LED panel that we used in 2007, and you can see it was handmade. And Bill Christens-Berry did a lot of that work, so there he is testing it. And so here we had an RGB sensor where we could get RGB at each pixel and illuminate it under different colors, so you get the coloration. And the interesting thing to me is when you get out to 870, the RGB filters are all transmissive, so you wind up getting a grayscale image. So there's the set of images we got, and there's you can see one of the forgeries, one of the icons that had text underneath it. So here's another observation we made. There's one of the undertexts, and in the infrared, that undertext showed up as bright, which was a complete surprise. We still don't know why. But a month later, we had a conference on the Archimedes in Budapest, and so Laszlo Horváth is showing that on the screen. Why am I showing you this? The enthusiasm of the scholar. So I'm sitting next to Sofia Kapitanaki from the University of Peloponnese. She's looking at the screen and transcribing it as fast as she can. So I took my camera and took a picture of what she didn't know. You can see how focused she is on reading that. The scholars just love the images. And here's the other one. So this is, Nigel Wilson was looking at this image, this pseudo-color image, and he said, I can read the name Aristotle. Fortunately, it was in the margin, so he was able to read it. The question is, why is there Aristotle in the Archimedes? And so Will Knoll sent us out a challenge saying, whatever you can do that would help us read that would be useful to do. And so a first-year undergraduate came up with the idea, and he did what he could do, not what I told him to do. He did not what he forgot I told him to do, and his result worked. So that was our eureka moment. You know, that was, I didn't run down the streets of Rochester at Christmas time naked, screaming, Eureka, Eureka, but we could have. And so let's skip the words and just go right to the image. So there is a section of that image in the gutter. And at the top, you can see a little bit of the undertext running horizontally. So we took that, broke it up into 3 channels, R, G, and B, and then we took those and did principal component analysis. So the first principal component is a weighted sum of those 3. It's in effect a grayscale image. The second principal component is the data projected onto an orthogonal axis. So what that meant was the dark undertext, overtext and the bright parchment got projected orthogonally to the same gray value. So in a sense, the overtext disappeared into the parchment, and all you're left with is the undertext. And suddenly you could read it. Totally unexpected. And so there's the before and there's the after. And Nigel Wilson says, go do the rest of them. And of course, they would have had to chain us down to keep us from doing the rest of them. That was really exciting. And Marwan Rashid at École Normale Supérieure in Paris says, please do the rest. And then we did a color angle rotation of those. So we took the RGB and made a pseudo-color out of it and did a U-angle rotation. So in the text in the gutter in the middle there, you can't see any undertext. But if we do a U-angle rotation, you can. So suddenly we're able to read other things, too. So we did the image processing on this through 2013, and now we're restarting it for the leads that Nigel wants. And we've sent a proposal to the owner to re-image 10 leads. So now let me do the X-ray fluorescence, because this turned out to be important, too. Uwe Bergman, who was then at the Stanford synchrotron source, is now he has a chair at University of Wisconsin. He was the guy who got us access to the system. And so there is the pseudo-color image of a stub in the middle, and there's the processed image. So suddenly we could read that. So, and we're doing more of that. We're going back to the Center for the Study of Manuscript Cultures in Hamburg and the Daisy in Hamburg to do this on some of the other manuscripts. I know I'm running out of time. So there is the appearance of one of the leads in 1906 that Heiberg took. There is the same leaf with the forged icon in 2007. So the idea is, how do we read that text? Well, we would use X-ray fluorescence. We would illuminate the page with X-rays. Some would be absorbed and re-emitted in at energies characteristic of the material. And so let me skip this. My cartoon on how it works. And so there we are in Stanford in March. So it's obviously not Rochester because there's blue sky. There's the setup. So we had the manuscript and we scanned it point by point and I had detectors around it. And so there it is being scanned. So we had a single beam, and so that's real time. That's how long it would take to scan, and we're doing 50 micron pixels here. And so there's the one we saw before, and there's the result. And here's one of the icons. The before, you can see the gold leaf on it. But with the X-ray fluorescence, you can see a significant amount of the text underneath. So that was fun, too. So the Archimedes was the place where we learned how to do this stuff. And as a result of it, we got a flood of invitations to do other things. It's important that well, let me skip this too. Let's say it was purchased by exactly the right person, because Mr. B was interested in reading it and he was willing to pay for it, and he was willing to allow us to experiment with his book. So when the book was reappraised, 5 years after he bought it, the value was estimated to be $7 million because of all the stuff we've been able to do with it. Okay, almost out of time. St. Catherine, tell you what, let me skip ahead, and I apologize. I knew this was going to happen, but I get excited about showing some stuff. I will jump ahead to the globe. This is the one, I'm going to do this one because this is one we've only done a couple sections. We want to do the whole thing. This is arguably the first globe ever made. So 1492, roughly, by Martin Beheim. And I just noticed I misspelled his name in the title there. So it's this big, and it's in effect made of paper mache, but it's parchment that has been erased and overwritten. So you can see it's writing everywhere on this thing. And this is in the National Museum in Nuremberg. Ken Boydston, our imaging guy, got the chance to image a couple sections of this in 2017. So there is a section of Africa, and you can see the water. And then here is down in the South Pacific. And so we did processing of that. So there's the Africa, did processing, there's the result. All the water has writing in it, and you cannot see it in the original. So we're hoping that they're going to allow us to go back and do the whole globe. Here's the other one. So you can see writing, just change the color scheme to show the writing. And there it is, one color scheme, and here's the same section, another color scheme, and completely different text. So this globe has all kinds of writing on it. They don't even know what it says. So we're hoping to go back to image that whole thing. I'll do one last one and then I'll quit. This is the world map of Martellus in the Beinecke Rare Book and Manuscript Library at Yale. And Beheim probably knew about this when he made his globe, and Columbus certainly knew about it. There it is, set up to image, and I'll just show this cartouche in the lower right corner of the map, because Chet Van Duzer, the scholar, had been trying to read this for years. So there were the images taken in the 60s that he was trying to read, and he said he could read a couple of characters. Well, we took the pictures, and 20 minutes later, I gave him that, and he said, I can read the whole thing, and it's really boring. So that's one of my favorite stories. Okay, so I have other pictures to show. If anybody's interested, we can talk about them. You can come on up, and we can talk about it afterward, but I should quit. So I'd be happy to entertain any questions.